All right, how's everybody doing here today? Let's give people another minute to get in here. All right, let me get started here. First of all, I put another homework set up for you guys. That will be, it should be up there now, and it's due a week from today. And that will be on the new material that we're starting, mostly chapter 7. So that'll be due on next Wednesday night, and it will help you practice some of the material that I'd like to put on the test, which will be the next class meeting on Friday the 24th. So just to clarify here, when I say the test is on Friday, I want to make sure that you guys can work on it at whatever time zone that you're living in. So I'm going to give you a 24-hour window to work on it. It probably will just take you an hour or two to finish. So choose in advance when you want to work on it. But keep in mind what the deadline. I'll probably ask you to have it done by 1 p.m. on that Friday. So I'll make it available, I guess, at 1 p.m. on the day before. So get all your questions answered before you, well, as you turn in the homework, I guess, and maybe Thursday morning as well. But then after that, it's once the test is out, then of course I don't want you guys discussing the test with each other. So that's it. So that the test will cover all that material that will be that we cover up through, I guess, up through and including that Wednesday. Do you have any questions on the homework that's due tonight? Anything that you guys need me to help you with? No?
Number 18 on the homework.
Hang on a second. Give me a minute to pull it up on my screen. I'm not sure I have it. Homework on homework 9, you mean? Preview. My computer is very slow loading it. Here we go. Problem 18. 18 is the very last one, right? So they ask you to evaluate this double integral, and they give you a bunch of inequalities to describe the set. I'll tell you what, let me write out the problem as it shows up on my screen, because you might have different numbers. I will adjust it to match your numbers. Oops, let me get, I don't know what you're looking at. I think I have this figured out by now. All right. So my version of the problem asks you to compute a triple integral over the set W. The integrand is x squared plus y squared to the 3/2. And the integral is taken with respect to volume. You'll be asking for the volume of pieces of this, where the set W is described in the same way, in the following way. You are told that the z coordinate is supposed to vary between x squared plus y squared, and I have 6 minus x squared plus y squared. And at the same time, you're supposed to have x squared plus y squared itself be less than or equal to 4, And they say down here that x needs to be less than or equal to, between -2 and +2, although that's actually redundant. I don't know why they mentioned that, because the previous inequality forces x to lie between 2 and -2. If x were bigger than this or smaller than that, then this x squared would already be more than 4. So adding a y squared to it couldn't give you something that's less than 4. Let me ask you this. When you tried the problem, how did you envision what this set looks like? W is described by these inequalities, but what does it look like? It's a subset of three-dimensional space. Did you get a picture? I forget who asked the question.
I tried, but I just couldn't successfully visualize it.
All right, well, let's do it together. So, so first of all, it's a subset of three-dimensional space, but it'll have a boundary, which is going to be some patches of surfaces. So you should expect when you see 1, 2, 3, 4 inequalities, your instinct is that you should expect to see, no, I'm sorry, did I count? 1, 2, 3, 4, 5 inequalities. You should expect to see 5 patches of surfaces that are glued together somehow to make the boundary of this set. Now I know, because I've seen this one before, it's actually not going to be 5, but that's what you would expect. So you would be expecting something like, I don't know, a little triangular pyramid, but maybe puffy so that the sides are not flat triangles. Maybe there'll be some pieces of spheres or something. All right, so we're going to try to describe this three-dimensional set by thinking about what the pieces of its boundary look like. We did this early in the semester, by the way. If you guys remember, you may have wondered at the time why I was giving you exercises of taking equations and visualizing surfaces, but now maybe you can see why this is important. So let's do it. Let me look at these inequalities first. Like I said, they're actually not really necessary, but let's see what they would do. If you want x to be between -2 and +2, the way that I encourage students to think of this is, why don't you change the inequalities to equations? When you do that, you will get actual surfaces in three-dimensional space. And those surfaces will split space into two sides, the two sides that are on either side of this wall. The inequality then is going to correspond to one side or the other of the wall. And when you have two inequalities, that means you have to be in the intersection of the two half spaces. So the equation x equals 2, for example, that specifies a plane. That one equation specifies a single point inside this one-dimensional space, just the x-axis. If you think about that as defining, think about this as an equation involving two variables. Now it's picking out a line or a curve in the two-dimensional xy plane. Two variables with just one equation that links them. 2 minus 1 is 1. It's one-dimensional. In this case, it's a straight line, and it happens to be this line in the xy plane. The fact that y wasn't actually mentioned in the equation means that I take my solution set in the lower dimensional space and I just stretch it parallel to the new axis. So that would be this line in the xy plane. And then you realize, wait, no, actually they meant this to be an equation of a surface in three-dimensional space. Now there's three variables, just one equation. 3 minus 1 is 2. It should be a surface. In fact, to get the surface, since z wasn't mentioned, I'll just take the picture I had in the lower dimensional space in the xy plane and stretch it in the direction of this new axis. So that gives me this vertical plane. So it's just a plane that's perpendicular to the x-axis passing through the point x equals 2. I'm sure a lot of you guys knew that, but I wanted to go through the steps because I'm going to use similar steps in the other surfaces. Likewise, this one. One more step. This is now the set of points where x is equal to 2. The set of points where x is less than or equal to 2 will obviously be one side or the other of this plane. And you can see, for example, the origin satisfies the inequality x is less than 2. So I must want the half of space that's on the back of this plane, the half of space that includes the origin. In exactly the same way, I could sketch the solution set to this equation. You can sketch the solution set either in R1 or in R2 or in R3. And when you're done, you'll have a plane that pierces the x-axis. It's pierced by the x-axis at the point x equals -2. We want, this inequality says we want half of space that goes up to the plane, and it's obvious that the half that we want is the half that's in front of that plane. So these two equations together say we should stay between those two planes. Now let's look at the next inequality. In the same way, I know it's written as an inequality, but I'm going to first sketch the equation x squared plus y squared equals 4. I'll throw those planes away because you'll see in a second I don't need them. So if you think of that equation as specifying a curve in the xy plane, you know that that'll be a circle of radius 2. And then you realize, wait, this was supposed to describe something in 3-dimensional space. One equation in 3 variables is a surface, and since the z wasn't mentioned, I simply stretch this parallel to the z-axis to get a cylinder. That's the set of points where x squared plus y squared is equal to 4. The set of points that have x squared plus y squared less than or equal to 4 is one side or the other of the surface. It's either the inside of the cylinder or the outside of the cylinder. I guess you guys know that, for example, the origin is going to satisfy this inequality. So we want the side of the cylinder that has the origin in it, and that means it's the inside of the cylinder. So from the 3 inequalities that are given at the end, I know that my surface is got to be inside the cylinder and on the behind this plane and in front of this plane. But since these two planes happen to be tangents, they are tangents to this cylinder. Oh, look, here I have a cylinder-ish. So one of the planes is here and the other plane is over there. So saying that you are between the two planes and inside the cylinder, that's just the same as saying you're inside the cylinder. So these were actually redundant. I don't know why they bothered to mention them. But this will be a part of the constraint that describes our set W. Now we have a couple of more constraints. So now let's look at this one. Where's the set of points where x squared plus y squared is less than or equal to z? Well, as usual, I'll begin by changing that into an equation. One equation, 3 unknowns, it's a surface. And I'm hoping at this point you guys recognize this one. It's actually a paraboloid. It includes the origin, 0, 0, 0, makes that equation be true. All the z-coordinates will be positive because you're adding squares. So all of the surface will be up above the xy plane. But if you piece together the level curves, which are circles, you'll see that this thing is actually a bowl. I'm sorry, I started to make it look more like a cone. That was bad artistry on my part. So you have this bowl that rises off the off the origin in 3-dimensional space. That's the surface where x squared plus y squared is equal to z. You need the part where you're on one side or the other. So you're either above the bowl or below the bowl. The inequality says you want z-coordinates that are bigger than the z-coordinates that are on the surface. So for each x and y, this equation tells you how far to get up to be on the surface. If you want a z-coordinate that's more than that, then you have to go above the surface. So this first inequality here says that you're supposed to be on the inside of this bowl. And when you combine it with the previous constraint, now you know that you have to be inside the bowl, but also inside the cylinder. So if you can envision a cylinder intersecting a bowl, you might be able to see that they meet at a circle. And the intersection now is going to be it's like having all the water that's down in this part of the bowl, but then But then when you go higher, you don't keep filling the bowl. At this point, you're just filling the cylinder. So it's a kind of a, I mean, it goes infinitely far up at this point, but it's just it's a long tube filled with whatever that kind of has a sort of a bullet-shaped tip at the bottom of it. One more. We have one more inequality that's going to be another part of the surface, the edge of our set, capital W. So we need the set of points where z is equal to 6 minus x squared minus, z is equal to 6 minus x squared plus y squared. And this is a set of points that has z coordinates all less than or equal to 6. You can't have a higher z coordinate if, because you're subtracting squares from 6. So the whole figure here is going to be bounded by this plane of points where the z coordinate is equal to 6. There's a top here. And from the top, the surface is going to have to come down, obviously, but it'll get wider as it comes down. You can visualize this shape a little bit by asking for how it meets, for example, the YZ plane. The YZ plane is a set of points where x is equal to 0, and if x is 0, you have the equation 6 minus y squared equals z. So that would be the graph of a parabola in the YZ plane. And it goes on both sides. In the same way.
The paper, please.
Oh, sorry, thank you. So in the same way, you could look at the intersection of the surface with the XZ plane. The XZ plane is a set of points where y is 0, and if y is 0, then the graph should be z equals 6 minus x squared, which is a parabola coming through the x-axis on two sides. So I think you can see that I'm actually building another bowl shape. It's like this one, but turned upside down. I mean, it meets the horizontal, the xy plane here, where the xy plane is the set of points where z is equal to 0, and having z equal to 0 and this as well forces you to be on a circle of radius square root of 6. So this is the graph of the other constraining surface. And once again, the inequality was given to you by saying that z is less than or equal to this quantity. For each x and y, the bowl that I've shown, the upside down bowl that I've shown, tells me the z coordinate that I would use if I want to get up to that surface. If we want to keep z coordinates less than that quantity, then we need to not rise all the way up to the top. So we want the stuff that's under this bowl. So now you need to take the previous shape and intersect it with this shape. You want to look at the portion of this that's also within this kind of a cap shape. Just before you get started, you might envision that it's one of two things. You could say, well, you've already got this circular pipe, and then you had to cut off a portion at the bottom. This is also going to cut off a portion at the top, so you might expect a shape like this. So I don't know how you would describe this. There's a little section of a cylindrical pipe with two roundish caps on the tops. These are not spherical portions, mind you. They're portions of a paraboloid, but it's the same kind of shape on the top and the bottom. I have to caution you, you might expect this, and this is in fact what you would have gotten, but only if they had made this number 6 be something larger. As it turns out, I mean, if I do exactly this thing with a 16 instead of a 6, you would get a top piece that looks like that one. But as you start replacing the 16 with lower and lower numbers, then you have to lower this, this cap, and eventually when it gets to be low enough, you find that there's no more of the cylinder left. In fact, when you keep lowering that coefficient that shows up in this spot, eventually you get it to be so low that the two the paraboloids actually intersect each other, and you can't even go that far away from the central axis. That turns out to be what happens in this particular problem because of the numbers that they gave you. You see, you've now got two paraboloids. Here's the one that went up, so this is where z is equal to x squared plus y squared. And then you have the other one that comes down where z is equal to 6 minus x squared plus y squared. I think you can envision that they will meet somewhere in a circle, but precisely where they're going to meet is where these equations are both satisfied. So you'll have z equal to two things at once, which will require that these two things be equal to each other, which forces x squared plus y squared to just be 3. So this is a set of points here where the x squared plus y squared would be equal to 3, and then both of these equations also force the z to be 3. So at a height of 3 units up from the xy plane, you draw a circle, you draw the intersection with either of these paraboloids, you'll get the very same circle. It's that circle floating 3 units up from the xy plane. And you notice that since 3 is less than 4, you'll never actually get to the edge of that tube, of that cylinder. All of these, the top of this paraboloid and the bottom of that paraboloid, they only stretch as far outward as this one circle whose radius is only going to be a square root of 3. You won't get out a distance of a full 2 away from the central axis. So like I crossed these things out before because they turned out not to be relevant, I should cross these out as well. They turned out not to be relevant either. Kind of a fluke, and it depends on the specific numbers. It may be that some of you guys got different numbers in this spot that would actually give you a shape like this one, but I think the random number generator in Quest gives everybody numbers for which this constraint turns out to be irrelevant. So at the end of the day, you don't need the two planes, you don't need the cylinder. All the action is just described by these two inequalities, because the solution set to just these two inequalities is already on the inside of the cylinder and it's already between the two planes. So your surface is actually just described by your set is described by two inequalities, and so its surface, its outside, is only found by patching together two pieces of a smooth surface. You stitch them together along that circle. So here's your set W at the end of the day. You can describe it as the set of points that lie over this bowl. This is the set of points where z is equal to x squared plus y squared, and it lies under this one, which is actually a mirror image of the one on the bottom, but it's turned upside down and raised to a height of 6 at the top. This is very, very timely, actually, because the easiest way to describe this is it looks like one of those plastic Easter eggs. Sorry, somebody had a question? Wu Yu.
I was just going to ask you to scoot up the paper, but you've already done so.
Okay. Wu Yu, you had your hand up?
Yeah, sorry. I was just going to make the comment that it's not true that everyone got numbers such that the cylinder is irrelevant.
I see. Okay. So exactly what that would require is if you got a number here which is less than half of the number that shows up over there, then your figure will look a little different. Yours will have this kind of tube in the middle. So yours isn't a plastic Easter egg. It's the two portions of the plastic Easter egg pulled apart with a little cylinder wrapped around the outside. And by the way, I was just sort of assuming that everyone would have the number that shows up in these two places would be the 2 square roots of that number. That's what made those planes irrelevant. But if this number is actually less than the square root of that number, then the planes would also be giving a further boundary to this. You would have to literally take this shape or this shape and slice off a portion by taking a saw blade that's perpendicular to the x-axis and have it chop off. Well, it would actually chop off a parabola there and a parabola there. Wow, now it looks like a Death Star. But I do want to emphasize it's not a sphere. The top and the bottom parts are both paraboloids. Now, since this was an integration problem, I guess I should say you should now be ready to start calculating your limits of integration. You could do it in Cartesian coordinates by saying you can have x's and y's that are anywhere inside this disk. That this is the disk now of radius square root of 3, because your x squareds and y squareds can never be, x squared plus y squared can never be more than 3. That one circle is the biggest that you'll ever have. And then for any combination of x and y that's inside this disk, your z coordinates can go from this number at their lowest. That's the z coordinate. If you start with an xy pair down on the floor, you have to go up at least this high to enter the plastic Easter egg, and then keep going higher and higher until you get to this z value, and at that point you've left, Elvis has left the building there. You've gone too high to be satisfying the inequalities. So your limits of integration, if you did it in Cartesian coordinates, would have x going from x squared plus y squared up to 6 minus x squared plus y squared. And then as far as the x's and the y's, I guess I would say if you did it in polar coordinates, your x could go from minus root 3 up to positive root 3, and then your y coordinate is bound by the two solutions of this equation. Once the x coordinate is fixed inside the circle, then your y coordinate, here's the rest of the circle, your y coordinate can only go from negative some square root thing up to the positive square root thing. Having said that, I think you guys probably know that this is an integral that's going to be easier to do if you do it in polar coordinates. So you would keep the same limits of integration on x, except you would phrase it in terms of r's. This would be 6 minus r squared, and that's just r squared. And the r's obviously would go from 0 to root 3, and the thetas would go from 0 to 2 pi.
I have a question. Is that I think this question can be like doing another method, like using the cylindrical
Yes.
system.
Yes. Yes, I said polar coordinates. I guess I should have said it's cylindrical coordinates, because this is a three-dimensional integral, so we need a coordinate system in three-dimensional space. And yes, I should have called it cylindrical coordinates, although you know that really it's the same as polar coordinates on the floor and Cartesian coordinates, and just the z-axis. The same z coordinate is used to go up. So yes, you're right. I should have said it's cylindrical coordinates. By the way, you could use Cartesian coordinates. It's just that it would be a horrible set of antiderivatives to do. You could use any other coordinate system. You want to use spherical coordinates? Have at it. You replace x, y, and z by some formulas involving rho and phi and theta, and you can figure out the range of thetas and phis and so on. And there's nothing wrong with doing it that way. It's just that you end up with some pretty awful looking limits of integration and some horrible antiderivatives to compute. So the mathematics doesn't care. You can use any coordinate system you like, but on a human level, that would not be a good choice. Cylindrical coordinates is the way to go on that one.
All right, Professor?
Yeah.
For those of us who had the cylinder, the only way I could have thought of computing the integral was splitting it up into 3 different integrals, like the top, middle, and bottom. How do you actually do it with only one integral?
No, even you guys. So let me take the case, or do you remember the numbers that you had for your inequalities?
Yeah, I had x squared plus y squared is less than equal z, less than equal 4 minus x squared plus y squared. And then the cylinder was radius 1.
Okay, so that's interesting. Yes, you do have something a little different. So the general part of the picture is the same. You've got this paraboloid that's going to form the bottom edge. That's the set of points where, where z is equal to x squared plus y squared. But then as soon as you get to the plane at a height of z equals 1, that's when the operating constraint is you need to have this expression. You need to stay within the cylinder where x squared plus y squared is equal to 1. And then that continues until you get to, let's see, when z is equal to 3, I guess, at a height of 3, then that cylinder is starting to intersect the other paraboloid. So you've got z equals 4 minus x squared plus y squared. right? Because when x squared plus y squared is equal to 1 and z is equal to all of this, then, wait, hang on. Yeah, if both of these equations, when you want to find that curve where the cylinder meets the top cap, you'll have both of these equations being satisfied, but if x squared plus y squared is 1, that means z is equal to 3. So that's another plane there. All right, so how would you do the problem? Well, I guess I would still use cylindrical coordinates. Inside this picture, you would first ask, what range of r's do you have? And remember, in cylindrical coordinates, r measures your distance away from the vertical axis. And it seems to me you can have r go anywhere from a minimum of 0 at the central axis to a maximum of 1 when you get to your cylinder. If you fix your value of r, that means look at all the points inside this figure that have a given r coordinate. And here, let me try to draw you the cylinder of points that has r equals a half. So that'll pierce this thing and stick out the bottom. Sorry, these should be straight lines that I'm drawing now. Okay, so there's a smaller tube that's piercing the original tube. That's the set of points that have a fixed r coordinate. Now within that set, what's your range of thetas? Well, that's easy. Theta just goes from 0 to 2 pi. Now hold a fixed theta coordinate. Remember, theta measures it's kind of the angle by which you've rotated a plane, a half plane around the central axis. So if I now hold the theta coordinate fixed as well, here's what I'm going to get. I'm going to look at, I'll draw you parts of it. Here's the set of points where r is equal to a constant, and I'm going to intersect that with the set of points where theta is equal to a constant. And that is now going to intersect my surface that had, first I have z is equal to 4 minus x squared minus y squared. And yeah, so the intersection will be right here. And this will continue down to the bottom paraboloid, where z is equal to x squared plus y squared. So when I hold both r and theta fixed, I should be down to a one-dimensional set, a curve. In this case, it's a straight line segment. And I need to know the least and the greatest values of the z coordinate anywhere on that set. Well, that's the z coordinate of this point on the one hand, and the z coordinate of this point on the other hand. So kind of irrespective of what r and theta I've chosen, r between 0 and 1, and theta between 0 and 2 pi, my z coordinates are going to vary from r squared, rather, up to 4 minus r squared. So there's your limits of integration. dz, d theta, dr, and I don't even remember what the integrand was. So it's really not any different. Even if your picture is different, you're still going to find the limits of integration in the same way. You said you wanted to split it into 3 sets, and you certainly might. In fact, you would be forced to do that if you decided to put dz on the outside. Mathematically, there's nothing wrong with that. But when I look at trying to describe the r's and thetas that go with a fixed value of z, you're going to get different answers depending on whether you choose a z that's less than 1, a z that's between 1 and 3, or a z that's more than 3. So you're right. You will have to have a split, a 3-way split, if you choose to put the z on the outside. So my answer to you in that case is either do it or choose a different order for your 3 variables so that you can avoid it. Is that clear? Did I make things any better?
Yeah, sorry, I just didn't consider.
No, that's fine. I mean, this is, so obviously, guys, I've been doing this thing for 3 times your lifespan. So I kind of know how some of these integrals will play out. And it's kind of easier to see in some circumstances which variables should go on the inside or the outside. Not that any of them is wrong, but some of them require different kinds of work. So you guys are just at a stage of you have to just do more and more of these to try to catch up with me. And after you've done, 1,000 or two of these triple integrals, then you'll have that same kind of intuition. But until you do that, until you get there, it's going to be some trial and error. And, it's not always clear which is going to be the best way at the end. All right. I'm glad you guys are asking some of these questions because I am going to ask you to do some of these on the test. And besides, it's a useful skill. That's why we're putting them in the course. But it's time for us to move into chapter 7. So let me tell you something about what's going on here. What we've been doing in the last few chapters, I don't remember where it starts, but up through chapter 6, is we had to compute integrals over chunks of Euclidean space. So we would either look at one-dimensional Euclidean space and integrate over some chunk of that, which means an interval, or in a two-dimensional Euclidean space, we might integrate over some solid chunk of two-dimensional space. And even in 3 dimensions, as the ones we've just done, we might ask you to integrate over a solid chunk of 3-dimensional space. Is that what I just drew? I don't know. Okay, but the point is that it's like solids. You can measure the overall length of this, the area of this, the volume of that. Starting in chapter 7, we're still going to be doing integrals, but they're going to be kind of mixing dimensions in the following sense. I might give you a picture in 2-dimensional space, but it will be a picture of a 1-dimensional object. That means that it's a curve, a portion of a curve. And I might ask you to integrate some function over this curve. In fact, I could do the same thing in 3-dimensional space. I could give you a curve that kind of wanders around and maybe wraps around the axes in 3-dimensional space, and then ask you to compute some integral there. Or I could mix dimensions 2 and 3 and present to you with some sort of a surface that floats around in 3-dimensional space and compute an integral over that set. Now, the idea behind the integration is actually not that exotic. It's going to be the same as every kind of integral that we've computed in the past. I will be forced to consider these things because for whatever reason, I'm going to be trying to compute something that feels natural. But the only way that I'm going to be able to do it is to take the curve or the surface and chop it up into little pieces and evaluate some number, some function on each one of these little pieces and multiply by the size of that piece. And on a curve, the way you measure size is by taking lengths. And on a surface, the way that you measure size is by taking areas. So I'll do it. I'll divide my set up and multiply the value of a function times the size of a piece, add those all up. And of course, I'll recognize that that's just an approximation to the real thing that I want to compute. To get the actual value of the thing I'm trying to compute, I'll have to take some kind of a limit, which will then turn that expression into an integral. So nothing really very, like I say, very exotic about that principle. In fact, let me try to show you a sort of a semi-realistic physical problem that would lead us into that situation. So here's the way I want you to think about this. It'll be an example of this setting. We're going to end up computing an integral over a curve that lies in the xy plane. And the way I want you to think about that is, here's the xy plane. And I want you to think about this as being a sheet of metal that's maybe just 1 centimeter tall. So I don't know how to make this start to feel like it has some thickness, but it does, okay? It's gonna be 1 centimeter thick, and it's gonna be metallic, but I'm gonna make this some sort of an alloy out of aluminum and lead. But I'm not gonna be able to mix this stuff very well, so I pour some molten lead over here, and I pour some molten aluminum over here, and I kind of use a brush to mush them together. But the stuff over here is mostly lead, and the stuff over here is mostly aluminum. And the consequences of it is that if you grabbed a little chunk of this thin sheet of metal and you measured the density, well, you would find that the density depends on the location that you are at in the xy plane. Now, I I messed this up with the previous class, so let me be careful. I'm going to measure my positions in the XY plane by drawing some axes and then measuring in meters how far I want you to go left and right, and then how far I want you to go up and down. And if you're at the position x comma y, let's suppose that the density turns out to be 5 plus x plus 2y. Okay, so down here on the aluminum end, the density right at the origin is 5. And by the way, I should give some units, huh? So let's have this be in something like grams per cubic centimeter. This is in meters. And you know, you go a meter over, and the density is now equal to 6 grams per cubic centimeter, and then it gets thicker and thicker as it gets more towards the lead side. In fact, if you go, I don't know, if you go like 7 meters out here, so let's have maybe if this is, let's call that, here's the x-axis. If you go 7 meters out, then the density would be 12. And in fact, there's other places where the density is 12. In fact, if you just go, I guess you'd have to go 3.5 meters here. 1, 2, 3, 4. So when y is equal to 3.5, then the density would also be 7 grams per cubic centimeter over here. And there's a whole line's worth of points where the density is 7 grams per cubic centimeter. And like I said, the density was 5 grams per cubic centimeter here, but there's another line of points where the density stays 5. Somewhere over here, the density has risen out to, I don't know, 20. Right? So the point I'm trying to make is that the density can be measured at each point. You will have these level curves. Along these curves, apparently I mixed the lead and the aluminum in a constant ratio so that you ended up with some intermediate density. By the way, I have no idea what the actual density of aluminum and lead is, so don't hold me to that. But as you move away from the origin, specifically if you move in that direction, you'll see that the density is getting steadily it's increasing density. All right, now here's what I want you to do. Take this thin sheet of metal, and I want you to do some careful cutting and take out a circular arc. So go up here to the set of points where y is equal to 7 and connect the set of points to the point where x is equal to 7 over there, and draw 2 cuts that are very close together. I mean like just 1 centimeter apart. So I will have created what I'm thinking of as a wire. It's not, you know, I asked you to make it be a centimeter by centimeter on its edge, but in the limit, I'm going to take those dimensions to get even smaller. Well, you can see what's going to happen. On the one end, you've got a mix of lead and aluminum. Over here, it's more lead, and then as you come over here, it turns into more aluminum. So the density is gradually shifting as you go. Here, the density is equal to 7. Here, the density is equal to 14. There's probably some points over here where the density gets to be close to 20. I don't know. But it's going to vary. So it's not immediately clear how you would get something like the overall mass of this piece of metal. It's basically a thin wire. But you know how you would estimate it, right? I mean, if the density is varying from a low of 7 to a high of 20, maybe, I don't know where it spends, I guess more of its time is spent with higher densities. I might eyeball the average density as being something like 15 grams per cubic centimeter. And as far as the volume of this piece of metal, well, it goes 1 centimeter this way and 1 centimeter that way, and it makes a circular arc. It's a quarter of a circle whose radius is 7 meters, that's 700 centimeters. So the length of this arc is something like 1/4 of 2 pi r is the radius, is the circumference of a circle. So that'll be pi over 2 times 700. So if that's the length, then in centimeters, then I get the total volume by multiplying the length times the other two dimensions. I mean, you could see, you could kind of straighten this out into a very long box. It's a 1 by 1 by something box. And the volume would then be 1 centimeter times 1 centimeter times this many centimeters. I guess that's 350 pi centimeters. There's your cubic centimeters. Here's your density in grams per cubic centimeter. And so I now can compute the mass. You get the mass by just multiplying all these numbers together. So it's going to be like 15 times 350 times pi grams. Now, you see the key thing is actually it's the variation in this one direction. I am not letting you go up and down too much or left to right too much. No matter how I measure anything else, any other curve, if I cut out another curve in a similar way, you'll have a 1 centimeter displacement here and a 1 centimeter displacement there. Those two numbers will just stay the same. They'll be multiplying this number of grams per cubic centimeter and effectively just removing the numbers of centimeters. So really what you should think about for that curve or any other curve in the XY plane, this rho is measuring what we would call a linear density. It's going to give you 5 plus x plus 2y grams per centimeter of length. So this is a concept that we can handle in a math setting because we are, we're buying our metal sheets in the same place where physicists buy their frictionless tables and inelastic spheres and stuff. So it sort of, logically speaking, the only thing you need to worry about is the density, the density as you march along this curve. And so if I have a curve whose total length is given here, I just multiply that number of centimeters by this number of grams per centimeter, and that'll give me this number of grams. Only it's really just an approximation, of course, because I had to approximate everything else. I got the exact length, but I don't have much of a feel for what the density is because it varies. It varies along the curve. Well, you guys know the obvious thing to do, if you want to get a better sense of the mass, is you should just divide this thing up into a bunch of little pieces and recreate exactly the same experiment on each little piece, because on any individual piece, the density can't vary quite so much. So we'll write this thing out as some sort of a limit of these approximations, a limit when the number of pieces gets bigger and the sizes of the pieces get smaller. In every case, you take a sum over all of the pieces of the linear density at some point in the piece multiplied by the length of the piece. Because that will give you the mass of the piece. Of course, you're never quite sure which point should give you the density, but as the pieces get tinier and tinier, then within any individual piece, the density can't vary very much. And so then it doesn't matter where you evaluate the density function. All right, well, to get the actual mass, you will take a limit of these expressions, and then what you'll discover is that you are just computing the integral of this density function with respect to length. The size of a piece means the length of the piece, and you're integrating it over this arc, this big circular arc. And if you capture the idea of what an integral means, then it's absolutely clear that this is the thing that's going to measure the mass for you. Of course, the problem with this is that it doesn't give us a sense of how exactly we could compute the integral. So let me give you the method that works for this. It's very similar to what we've been doing with the change of variable theorem. I've been emphasizing this idea of parameterization, and that's what you need here too. Because if you take this circular arc and you say, I want to split it into some pieces and then choose points where I'm going to evaluate the density function, here's my recipe for how you should do that. Why don't you take a range of numbers in a copy of the real number line? Let's take, how about the numbers that go from 0 to pi over 2, and map them onto that circular arc with a parameterization of that curve. This is exactly the kind of thing that I've been calling capital T in the change of variable theorem. I'll stick with the book's notation of using the letter phi now. But the parameterization that would take these numbers and give me all the portions of the circular arc would be to take the x-coordinate to be 7 cosine of t, and the y-coordinate to be 7 times the sine of t. Then, this parameterization allows us to do the kind of thing we need in an integral. If you want to split that arc up, just split up this interval into little pieces and find out where each one of those little pieces goes over here. You have to choose a representative point of each piece? No problem. Just choose a little representative point inside each one of those little intervals. Now, you're supposed to evaluate the density function right here, but if each one of these points is phi of one of these points, then I can evaluate the density, do all of my calculations right over here with a bunch of t's. That literally, the formula for what I'm computing is the composite rho composed with phi. That's the function that takes the number t and it does what you would naturally want to do. You take the number t and you first compute phi of it to get your x and y coordinates. That's these two numbers. And now that you have the x and y coordinates, just shove them into the density calculation to get 5 plus 7 cosine of t plus 14 times the sine of t. And that'll allow you to evaluate the density function at each one of these points, but doing it with just the t values over here. So you kind of don't even need to look at the arc. But you're supposed to take those measurements of the value of the density function and multiply them by the sizes of each one of these arcs. And that's where you have to be careful, because these arcs are not the same lengths as those arcs, those little line segments. Here's the fact that you need. Lengths in this parameterization, lengths are stretched by a factor of, here you go, take this parameterization function and differentiate it. And this is a function that goes from R1 to R2, so this is going to be a 2-by-1 matrix. It'll be a vector in R2. And I want you to give me the magnitude of that vector. That'll be a positive real number, and it gives me exactly the stretch factor that says how lengths here are turned into lengths over there. What that'll do for you is when you say, well, I'm supposed to multiply by the length of this line segment, I'll say, just multiply by the length of this line segment and then throw in that extra factor. And here's your conclusion. This is your recipe for how to compute the integral of a function like the density with respect to length over really any curve. After you've parameterized it using an interval in the real number line, you have to just integrate over that interval the function that I just wrote out. That's rewriting the integrand. And then to rewrite the differential, to take into account the lengths of the pieces that are on the actual curve, we'll take the lengths of the little intervals in this picture and we'll multiply them by the stretch factor. So this becomes our method for how we would ever actually compute those integrals. The first part of my discussion was why this is a natural thing to compute in terms of separating, adding together products of values of rho times the length of a piece. But in terms of actually calculating it, you begin by finding the parameterization that parameterizes your curve over a little interval. In our particular case, this derivative is easy enough to compute. You just differentiate the x and y components. And then when you look for the magnitude of this vector, you'll just pick up an extra factor of 7. So all you have to do is integrate the function that I had written down earlier and multiply that by this extra factor of 7 and integrate with respect to t as t goes from 0 to pi over 2. So I'm out of time, I know I've gone over. I invite you to actually calculate the integral and get a numerical value and compare it to what I got when I was just eyeballing things in the first place. I got some sort of estimate for what I thought the mass would be. See if you don't get the same or a comparable number for this integral, and you'll see that I've actually computed the integral, the mass, in a pretty natural way. All right, how about if I quit here, but when we get together on Friday, this is exactly where I want to pick up. I want to do some more examples with you. Try some that are in the new homework, try some that are in the end of section 7.1. We'll do these again on Friday, and I'm going to actually skip 7.2 for the time being, just for probably 1 or 2 days, so that I can show you that we can do a comparable thing for surfaces as well. Anybody want to ask me a question? I know I'm over, but no? All right, give it your best shot, guys, and bring me some more questions on Friday. I guess I didn't even need to do that. Oh, Yangzhu, you have a question before we go?
Yes, I want to make sure, what is the range of the test on 24?
It will be everything that we're doing between now and next Wednesday. It's going to cover all the way through, well, from where we left off on the last exam, all the way up through what we're doing now, and it'll be probably the first few sections of chapter 7 as well.
Like 7.3 and everything above 7.3?
7.1 is what we're doing today. We'll do it again on Friday. 7.3 we will do on Friday. The one that's a little iffy is whether we will have time to get back to section 7.2. But I think so. I think we'll be able to do maybe as much as 4 sections of chapter 7 by the exam.
Okay.
You guys can do it. You guys can do it.